I'm Abby.
And I'm Rose.
And today we're going to talk about game theory.
Now, most people would ask, what is game theory and what does it have to do with math? Game theory sounds scary or fun, depending on if you're really into games.
Game theory is actually a type of game if you think about it. However, it's officially known as a branch of mathematics concerned with the analysis of strategies for dealing with competitive situations where the outcome of a participant's choice of action depends critically on the actions of other participants.
Game theory is a branch of math, but it can and has been applied to contexts in international relations, business, economics, and biology. This goes to show the diversity of game theory even if it stems from the world of math.
It involves logic and probability to determine the course of actions a player can take.
Although game theory can be used to determine complicated trends in economics, stocks, wars, and more, we can use game theory to help us make everyday decisions.
We're not all going to have to make complex war or stock exchange decisions, so here's an example of basic game theory where we as college students can all relate. Should you be nice or mean to your roommate if he or she is not clean or dirty?
What we see here is a basic game theory tree, where we have decision nodes, which are a point of the tree where we see a player can make a decision actions, what a player does at each decision node. There's also a payoff, which is what each player gets at the end of the game.
Some assumptions we have to keep in mind is that all players are rational, so all players will choose actions that give them the highest payoff at the end of the game.
We see that if the roommate is to be clean, they will get a 3 for a payoff because they know you will choose to be nice. Because if you choose to be mean, your payoff is a 3. While if you're nice, you will get a 4. 4 is greater than 3, so you will be nice.
Knowing that you will choose to be nice, the roommate will get a 3 if they are clean.
We see that if the roommate is to be dirty, they will get a 4 for a payoff because they know you will choose to be nice. Because if you choose to be mean, that your payoff is a 2. While if you choose to be nice, you get a 3 for a payoff. 3 is greater than 2, so you will choose to be nice.
Knowing that you will choose to be nice, the roommate will get a 4 if they are dirty.
Because 4 is greater than 3, the roommate will be dirty knowing you will be nice either way. And by being dirty, they get a higher payoff than being clean anyway, which is in their favor.
Now we can use these equations on the screen to find out what is called the expected payoff, which helps us choose which actions to take. The expected payoff is what the player is expected to get overall after the game is finished. Just now we decided that the roommate would rather be dirty than clean, because the payoff is 4, which is greater than 3.
We can find this expected payoff through an equation where P represents the probability that the roommate will choose being clean. Expected payoff clean equals P times the highest payoff of being clean plus 1 minus P times the lower payoff of being clean, where the expected payoff of dirty equals P times the highest payoff of being dirty plus 1 minus P times the lower payoff of being dirty. In this example, EP clean equals 3 and EP dirty equals 4.
We write P as 1 because we know that if we look at the probability in terms of fractions, we know that the roommate, knowing you will choose to be nice, the roommate is 100% sure they will get a 3 for a payoff. So in our expected payoff equation, we do 1 times 3 and 1 minus P, which is 0 times 2, because the roommate knows for certain that they will never get a 2 as a payoff because you will always be nice over mean.
If you add the probabilities and payoffs, we see that the EP of being clean is 3, while the EP of being dirty is 4. Therefore, we are able to mathematically solve what the roommate should do.
In game theory, there is something called a strategy pair, which is a listed strategy that says what each player is going to do.
For example, a strategy pair of this game is clean, semicolon, nice, comma, mean. What goes before the semicolon is the roommate's action, and what comes after is what you do in response to that. What this means is that if the roommate chooses clean, then you will choose to be nice. If the roommate chooses to be the opposite, in this case dirty, you will choose to be mean. Essentially, the two options following the semicolon are the two branches of the tree. What goes before the semicolon corresponds with what branch of the tree it is.
Another strategy is dirty, semicolon, nice, comma, mean. In this case, if it means that if the roommate is dirty, you will be mean. If the roommate is clean, you will be nice. We see that the clean branch is above the dirty branch, so the clean branch is the upper branch, and the dirty branch is the lower branch. In the strategy pair, what you do, nice or mean, is separated by a comma. The first action before the comma is called the first decision node, which will always correspond to the nice branch, and what is behind the comma, or the second decision node, is what will always correspond with the dirty branch. The action in the first decision node will always correspond with the upper branch, and the action in the second decision node will always correspond with the lower branch in any game.
In the picture, we see that the first decision node, underlined in pink, will always be the response to the upper branch, or clean in this case. The second decision node, underlined in purple, will always be the response if the response to the lower branch, or dirty.
So that now that we know what game theory, actions, and strategy pairs are, we can break it down further. The form of game theory we will be working with today is called perfect and complete information. In each game there are strategies or a decision plan that tells a player what he or she will do at every decision node.
Nash equilibrium, where in a game with two players, is a strategy pair such that no player gains from unilaterally changing her strategy. Basically, by holding the other player's strategy fixed, a player cannot increase his or her payoff by changing his or her strategy. Subgame perfect equilibrium, which is the same thing as Nash equilibrium, but where neither player is not bluffing or lying about what decision he or she will logically make.
We see here that a no equilibrium strategy pair is when the strategy pair given does not give a high payoff for anybody. We see that the strategy given shows that the roommate should choose to be dirty over clean, holding your strategy constant as mean, nice. Therefore, the strategy is already at no equilibrium.
We see here that the roommate could raise her strategy by being dirty instead of nice, as 4 is greater than 2. As the strategy pair lists that the roommate should be clean, the strategy pair is wrong. Therefore, this is no equilibrium. Looking at the strategy pair chosen at random, we see that if the roommate is clean and you are nice, the payoff is 3 for the roommate and 4 for you. If we continue with the given strategy pair, we see that if the roommate chooses dirty and you choose mean, the roommate's payoff is 1 and yours is 2. So far, holding your strategy constant that you will play nice with clean and mean with dirty, the roommate should choose clean.
Continuing with the strategy pair, if we hold that the roommate is clean and you play mean instead of nice this time, the roommate will get 2 and you will get 3. As the payoff of being nice is 4 and greater than the payoff of mean, 3, you should be nice. As the strategy pair lists clean, nice, mean as the ultimate strategy to play, we see that no one is able to raise their payoff by unilaterally changing their actions, holding the other person's actions constant. This is Nash equilibrium.
However, the last strategy pair we showed is not subgame perfect, although it was Nash equilibrium, because there is a bluff. If you were to be nice instead of mean when your roommate was dirty, you could have raised your payoff from 2 to 3, and your roommate could have had 4 instead of 3 for a payoff. By claiming to choose mean over nice when the roommate is dirty is a bluff. It's a lie. It would not be rational to choose mean over nice if it would lead to a lower payoff. Therefore, the strategy pair that would have been subgame perfect would have been dirty, nice, nice. By seeing that you would be nice no matter what, the roommate would choose 4 over 3 payoff and be dirty. Holding the roommate to choose being dirty, you will choose to be nice over mean as 3 is greater than 2.
There is no way to get a higher payoff for both actors holding each other's strategies as constant. So this strategy pair is subgame perfect Nash equilibrium, the best strategy pair where all the players get the highest payoffs possible. We now understand how basic game theory works. However, how can we apply this to a bigger real-life situation?
We created a two-tree game to explain the current conflict going on between Hong Kong and China, also known as the Umbrella Movement. But before we go into the game, we're going to give you a little background information we learned that help us develop the game and determine payoffs. So we all know that Hong Kong is a part of China. However, China's control of Hong Kong is relatively recent. For 156 years, Britain controlled Hong Kong. Britain trying to control and colonize a place they have no right to be in? Preposterous. In 1997, when the People's Republic of China took control over Hong Kong, one of the main aspects of the country's agreement was the concept of one country, two systems. That is, they would be united together as a country, but each would have their own system of government, so that Hong Kong could retain their own government and rule themselves.
Hong Kong, having been under British rule during the beginning of the development of the People's Republic of China, had developed into a very different type of place than mainland China. They had a democratic system of local government, free press, and just a general social culture that had been influenced by Britain.
China had assured Hong Kong that they would not meddle, and that Hong Kong could retain their self-sufficient government for at least 50 years, and that the people of Hong Kong would not be subject to the same laws and regulations as the people of mainland China. This was okay because Hong Kong was called a special administrative region and not necessarily a state. However, in the past years, tensions have risen as Hong Kongers fear that mainlanders are stepping over their boundaries.
Although they still technically have freedom of press, the mainlanders have gotten control of several main media outlets and often censor or propagandize the content. To add insult to injury, many common practices of mainlanders seem offensive and rude to Hong Kongers, and vice versa, only furthering the rising tensions and heated feelings.
So what is happening now? Protests. Hong Kong is getting ready for their first election of their own leader, set to happen in 2017. Because of one country, two systems, Hong Kong wanted to have open nominations for candidates. However, Beijing stepped in and rejected this proposal. Instead, Beijing is proposing that the candidates be chosen by a special committee, and obviously they plan on choosing who is on that committee, and thus the candidates will be more pro-mainland than pro-Hong Kong. This obviously violates the one country, two systems agreement, which threw Hong Kongers into a fury.
However, China is in a bit of a pickle. They fear that leaving the protesters just let off steam will cause mainlanders to become more emboldened and make the government look weak. However, because Hong Kong has freedom of press, they do not want to crack down too harshly on the protests for fear of the global visibility of any of their actions.
Hong Kong, on the other hand, doesn't want to back down for fear that this is just the beginning of China coming in and taking control of their government. As protests gain momentum, various people have emerged with different ideas of what Hong Kong should do. C.Y. Leung, a top businessman in Hong Kong, continues to advocate that the protesters withdraw, while Benny Tai Yongxing, a professor at University of Hong Kong, is promoting a peaceful protest movement which has been dubbed Occupy Central.
The man who has gotten the most media coverage, though, is Joshua Wong, a student who played a huge role in leading the beginning protests, as protests began as a student movement before they gained steam.
So why should we care about the protests? As NYU math students, why should we bother using game theory to try and predict outcomes?
Chinese pro-democracy demonstrators have taken to the streets in Hong Kong, and the Chinese media, state-owned media, has said that it's all the fault of the Americans. Joining us now to make some sense of this is Dr. Michael Pillsbury, a senior fellow of the Hudson Institute and former Reagan administration official. Thanks for joining us. So what do you think? It's all the Americans' fault?
It's not all our fault, but we're partially involved. We have a large consulate there that's in charge with taking care of the Hong Kong Policy Act passed by Congress to ensure democracy in Hong Kong. We also have funded millions of dollars of programs through the National Endowment for Democracy to help democracy in Hong Kong. So in that sense, the Chinese accusation is not totally false.
I can tell you that the U.S. government is closely watching the situation in Hong Kong. Around the world, this is true in Hong Kong and other places, the United States supports internationally recognized fundamental freedoms, such as the freedom of peaceful assembly and the freedom of expression. The United States urges the Hong Kong authorities to exercise restraint and for protesters to express their views peacefully. The United States supports universal suffrage in Hong Kong in accordance with the Basic Law, and we support the aspirations of the Hong Kong people. We believe that an open society with the highest possible degree of autonomy and governed by the rule of law is essential for Hong Kong's stability and prosperity. Indeed, this is what has made Hong Kong such a successful and truly global city to this point.
So what plans of action should China and Hong Kong take? Let's apply the game theory to see which actions will have the better outcome for both parties.
If we think about our roommate situation, you decided to be very nice no matter what if your roommate was dirty or clean. However, in another game, you could have been very mean. This is because of an element in game theory called nature. Nature will decide P, the probability of you being nice, versus 1 minus P, the probability of you being mean. In another scenario, nature could have determined that you were in a bad mood versus a good mood. We leave nature to determine how payoffs are determined, which allows more accurate predictions of real-life situations, as the nature of a country can be unpredictable, which can change how the other nation reacts. In the two-tree game we're about to show you, we see that P is where Hong Kong is more aggressive, and game 1 minus P is Hong Kong being less aggressive.
In the two-tree game we're about to show you, we see that game P is where Hong Kong is more aggressive, and game 1 minus P is where Hong Kong is less aggressive. Essentially, if the protests in Hong Kong are aggressive, they will be very loud, inspiring, motivational, and influential to pro-democracy mainland Chinese, whereas if they are not aggressive, they will have minimal impact for their own agenda and on the aforementioned mainlanders.
This is the two-game tree we created. We are now going to explain how we determine the payoffs we assigned. Thinking about if nature decides that Hong Kong protests are going to be aggressive, we see that should China negotiate and Hong Kong continue to protest, China will get 4 and Hong Kong will get 8. This is because if China negotiates and Hong Kong still protests, Hong Kong will be heard and will get the leader they want. And China gets a lower payoff because they had to compromise and they still risk mainland Chinese incitement from the protests.
Should Hong Kong not protest in response to Chinese negotiation, China gets 7 and Hong Kong gets 7 because China won't have to worry about mainlander being influenced by Chinese protesters, and Hong Kong gets the leader they want.
In the same aggressive tree, if China doesn't negotiate and Hong Kong continues to protest, China gets -3 and Hong Kong gets 5 because China risks high influence of mainlanders being by upset protesters, as well as facing public scrutiny from the Western world, while Hong Kong doesn't get the leader they want, but they still raise the awareness of the problems in the situation to the rest of the world.
Should China not negotiate and Hong Kong not protest, China gets 8 and Hong Kong gets -4, because China will not have to compromise and won't become the public enemy, whereas Hong Kong won't get the leader it desires and fails to publicize the problems they face.
The second tree is nature deciding that the protests are not aggressive. We see that if China negotiates and Hong Kong protests, China gets 2 and Hong Kong gets 7. Because if China negotiates, they have to compromise, but if the Hong Kong protests are more influential, as they would be if nature decided aggression.
If China negotiates and Hong Kong does not protest, then China will get 6 and Hong Kong will get 5, because if China negotiates, again, they have to compromise, and now they don't have to worry about protests inciting mainlanders.
Should China not negotiate and Hong Kong protests non-aggressively, China gets 3 and Hong Kong gets 4, because the Chinese wouldn't worry about the protests inciting the mainlanders, but they would still face scrutiny from the Western world, whereas Hong Kong wouldn't get the leader they want and wouldn't have a strong effect on the people of China.
Should China not negotiate and Hong Kong not protest, China gets 9 and Hong Kong gets -2, because China has nothing to worry about and they haven't compromised anything, while Hong Kong faces losing its leader and in turn media coverage, freedom of press, and harmful potential future with pro-Chinese leader as the head of the governmental system.
Now that we've seen the two-tree game, we are going to use backwards induction to find the subgame perfect Nash equilibrium as the best strategies China and Hong Kong can make from each game. Although Nash equilibrium strategy pairs are important, subgame perfect Nash equilibrium strategy pairs will show the best outcomes of the protests for both China and Hong Kong without any bluffs from either country.
To start backwards induction to find the subgame perfect Nash equilibrium for the first game P, where Hong Kong is more aggressive, we need to look at the overall payoffs listed at the end of the game. We see that since Hong Kong makes the last decision of the game, we need to see what their highest payoff for Hong Kong is when China negotiates. We see that Hong Kong gets a slightly better payoff of 8 rather than 7, so we see that in game P, when China negotiates, Hong Kong will always protest over not protest.
When China does not negotiate, we see that Hong Kong gets a significantly higher payoff of 5 rather than -4. So we see that in Game P, when China does not negotiate, Hong Kong will always protest over not protest. Holding that Hong Kong will always protest no matter what in Game P, China is left to decide whether or not to negotiate or not negotiate. If they negotiate, China will get a payoff of 4. If they do not negotiate, they will get a payoff of -3.
Therefore, in Game P, China will negotiate, holding that Hong Kong will be rational and protest to get the better payoff. We see here that when Hong Kong is more aggressive in protesting, the subgame perfect Nash equilibrium is negotiate, semicolon, protest, comma, protest. In this strategy pair, we see that neither country is bluffing when China chooses to negotiate and Hong Kong chooses to protest. They will both get the highest payoffs. There are no bluffs because Hong Kong would truly choose to protest if China were not to negotiate.
In the second game, 1 - P, where Hong Kong is less aggressive, we see that when China negotiates, Hong Kong will choose to protest as 7 is a greater payoff than 5. When we see that China does not negotiate, Hong Kong will protest as 4 is a greater payoff than -2. Therefore, Hong Kong will always protest no matter what. Holding that constant, China must choose to negotiate or not negotiate. In this case, if they negotiate, their payoff will be 2. If they do not negotiate, their payoff will be 3.
Therefore, in Game 1 - P, China will not negotiate and Hong Kong will protest no matter what. In this game where Hong Kong is less aggressive, the subgame perfect Nash equilibrium is not negotiate, semicolon, protest, comma, protest. Looking at the payoffs, neither China or Hong Kong can raise their payoff by changing their strategy holding the opponent's strategy constant, and neither country is lying in their strategy pair.
Now that we know that in the case when Hong Kong is more aggressive, the best moves for both countries is to negotiate and protest, and when Hong Kong is less aggressive, the best moves for both countries is to not negotiate and protest, we can find something that is called the indifference to find which game is the true game. Indifference in this case is to find the probability that would leave China indifferent between negotiating and not negotiating. That way we can find the actual percentage that it takes P or 1 - P to be the true game.
We do this by finding the expected payoffs for China negotiating and not negotiating in both games and set the two equations equal to each other to find the percentage of probability that determines which game is true to determine which strategies are best for both countries.
From finding the subgame perfect Nash equilibrium from earlier, we already know that when China negotiates in both games, the best payoffs are 4 and 2, holding Hong Kong's strategy as constant as protesting. And we already know that when China does not negotiate in both games, the best payoffs are -3 and 3 when Hong Kong's strategy is held as protesting. When we set up the equation, we put P times the payoff of negotiating in Game P plus 1 - P times the payoff of negotiating in Game 1 - P. In the other equation, we put P times the payoff of not negotiating in Game P plus 1 - P times the payoff of not negotiating in Game 1 - P. It overall comes out to be P times 4 plus 1 - P times 2 for the expected payoff of negotiating in both games, and P times -3 plus 1 - P times 3 for the expected payoff of not negotiating in both games. To find the indifference, we set the two equations equal to each other to find that 2P plus 2 equals -6P plus 3, so P is 1/8.
Now that we know the indifference P is 1/8, we can use substitution to find out which is the true game.
When we substitute a number such as 1, which is greater than 1/8, into the expected payoff equation, we see that the expected value for negotiating is higher than the expected value of not negotiating. This means that when the probability of Hong Kong being aggressive is over 1/8, China should negotiate as decided by the subgame perfect equilibrium earlier, as the strategy pair determined was negotiate, semicolon, protest, comma, protest. As negotiate has a higher payoff when P is greater than 1/8, game P is the true game in this case.
When we substitute a number such as -1, which is less than 1/8, into the expected payoff equations, we see that the expected value for the not negotiating is higher than the expected value of negotiating. This means that when the probability of Hong Kong being less aggressive is less than 1/8, then China should not negotiate it as decided by the subgame perfect equilibrium strategy, not negotiate protest, protest. As not negotiate has a higher payoff when P is less than 1/8, game 1 minus P is the true game in this case.
By finding indifference, we are able to see which game is the true game and therefore what each nation should do. By substituting a number greater than 1/8 into P in the equations to find the expected payoffs, we're able to see that when P is greater than 1/8, game P is the true game, and when P is less than 1/8, game 1 minus P is the true game.
In conclusion, we would like to stress that although our payoffs may not be entirely accurate, they were decided on real factors that influence how China and Hong Kong would make their action choices. By using math, rationality, logic, algebra, and probability, we are able to see that the best outcomes for both countries in this sticky situation can be determined.
We hope you've enjoyed this video and our application of game theory and math in the real world. Thanks for watching!